Enough about the gravitational potential energy. We move to a second form of potential energy, which is the spring potential energy. We are all familiar with springs. Imagine a spring fixed at one point and free at the second point. Now, if you act on this spring by a force here, as you can see, so now there is a compression by X. There is a compression by X. You are storing energy. You are doing work. The spring now contains potential energy equals half kx squared. K is a proportionality constant. We call it spring constant. And x is the displacement. Kinetic energy is zero. There is no motion involved. Then if you let go, the potential energy stored in the spring act and will convert into kinetic energy, such that when the spring is returned to its original uncompressed position, x equals 0, the energy is all kinetic. It's half mv squared. So this is another form of energy which depends on the relative position as we have for the gravitational potential energy. But now we are talking about spring force rather than gravity. When we deal with spring force, we need to use Hooke's law. Hooke's law tells us that whenever you compress or stretch a spring, there will be a restoring force as we call it, that tries to restore the spring to its original unstrained shape and position. And this restoring force is proportional with the displacement x, and the proportionality constant k is called the spring constant. Okay? We will need the spring constant always when we deal with the springs in order to calculate the restoring force or to calculate the spring potential energy. For the full cycle, as you compress the spring, you'll be dealing with the average force. The average force is equal to the initial force plus the final force divided by 2. This is the average of two forces. Initially, there was no compression, so the force was 0. When you compress it, the force is minus kx divided by 2. So the average force is minus half kx. Now, according to the work equation, force by displacement, it is half kx multiplied by x. So you have half kx squared. That is the work done in this situation. And this is equal to the change in the potential energy, half kx squared final minus half kx squared initial. Okay? So the change in the potential energy is equal to the work done against the spring. Since we have motion also in addition to the potential energy, so the work now needs to include all terms. So the work here is equal to the change in the kinetic energy plus the change in the potential energy. This is the generalized formula now for the work energy theorem. Work done against non-conservative force, if there is friction, is equal to the change in kinetic energy plus change in gravitational potential energy plus change in elastic or restoring force potential energy. We call this property of springs to restore their original shape, we call it elasticity. And the restoring force is called also elastic force. So now we have three forms of mechanical energy that we learned so far: kinetic energy, gravitational potential energy, and spring potential energy. We learned how to calculate each one of these three energies. For the spring, as it exchanges the energy from potential into kinetic, if the height does not change, so you don't need to worry about the gravitational potential energy. If you are working with a horizontal system, you need only to worry about the conversion of energy from elastic potential energy into kinetic energy. Calculate the elastic potential energy of a spring with spring constant 225 Newton per meter that is compressed by 1 centimeter, 1 by 10 to the minus 2 meter. In this case, the elastic potential energy is half kx squared. X is the displacement from equilibrium. When it is compressed by 1 centimeter, x squared is 1 centimeter by 1 centimeter. This is 10 to the minus 4 squared meter. We have to use SI units. For x, it is meter, not centimeter. So the potential energy in the ring is half kx squared. Half k is 225, and x squared 1 by 10 to the minus 4. This is 1.13 by 10 to the minus 2 joules. The elastic potential energy of a stretched or compressed spring is always positive. You may have noticed that the elastic potential energy is equal to half kx squared. So we are not dealing with x, we are dealing with x squared, which means if x is negative or x is positive, it doesn't make a difference because we are dealing with the square of x. So yes, the elastic potential energy is always positive. Elastic potential energy depends on the spring constant and the distance the spring is stretched or compressed. By what factor does the elastic potential energy change if the spring stretch is doubled? So if you are doubling x because it depends on x squared, then the change in the energy will be quadrupled. Using the same example, but now the change in the spring stretch is tripled. If you triple the value of x, then for the energy, it would be 3 to the power 2, which is 9. So the energy will be 9 times greater.